Hello, this is transformation of stress example number 3. The problem reads, for the state of stress shown below, determine the maximum shearing stress when sigma z is equal to 0 megapascals. Use a Moore's circle drawn for the state of stress to illustrate the process of determining the maximum shear stress. We're going to expand on this a little bit and use a Moore's circle to also find the maximum principal stress, minimum principal stress, and we'll also look at it to find the stress on a plane that's rotated by some angle, say theta equals 40 degrees. Now, I want to point out that this example here says that sigma sub z is equal to 0 megapascals. Your handout might include a different value of sigma sub z, but for right now, we're going to use it for sigma z equals 0 megapascals. And that's important because when sigma sub z is equal to 0 megapascals, that represents a state of plane stress. All right, so let's go over to OneNote and start working there. But before we do it, let's take a look at the stresses we have. We have sigma x is equal to 30 megapascals. We have sigma y is equal to 60. And tau xy is equal to 36, sort of. Let's go to, there we go, OneNote. So what I'm going to do is I'm going to start off by drawing my differential stress block over here in OneNote, and I'll draw it like this. And actually, let me move it over to the right a little bit so we have it like that. Okay, now the stresses that we have are like this. This is going to be sigma x, and sigma x is equal to 30 megapascals. We have a stress here, sigma y is equal to 60 MPa, and that also goes down like that. And then we have a shearing stress that's on here, and I'll be a little bit different with this. I'll say that tau xy is equal to 36 megapascals. But remember that if the shearing stress points to the upper right corner, then that would be considered a positive. But since it points to the lower right corner instead, that this shearing stress is actually negative. So let me just, to be clear over here, I'll write that sigma x is equal to 30 megapascals positive. Sigma y is equal to 60 megapascals, also positive, and then tau xy is equal to 36 megapascals. That is negative, and I left an A off there. All right, so what I'm going to do is use my Moore's circle to illustrate the different stresses that are on this section. So I'm going to draw the Moore's circle first. So the first step is to determine a set of coordinate axes. So in this case, since both sigma x and sigma y are positive, I know that the Moore's circle is going to lie to the right of the vertical axis, or at least primarily to the right of the vertical axis. So let me go ahead and sketch my vertical axis like this. Vertical axis is always the tau axis. Then I'm going to have a horizontal axis that goes like that, and that will be my sigma axis. All right. Okay, taking a second and cleaned up this, the lines a little bit, drew them a little with a straight edge so that it looks a little bit nicer. And I'm going to look here at my scale, and I know I have sigma y is 60, sigma x is equal to 30. So I'm going to choose a scale that is 1 square is equal to 10 megapascals. Now, it takes a little bit of experience to be able to pick a good scale like that, but you can kind of guess how big the circle is going to be based on what sigma x and sigma y are, along with tau xy. So I'm going to use a scale of 1 square is equal to 10 megapascals. So step number 1 is going to be to plot sigma x comma minus tau xy. That's either the first step or the second step, depending on which version you look at. In other versions, step 1 is to draw the axes. So sigma x is equal to 30 megapascals, and tau xy is equal to a minus 36. So 30 megapascals. So I go over here, 1, 2, 3, and minus tau xy is equal to a positive 36. So I go up 1, 2, 3. Right there is about 36. So that is going to be plus 30, comma, plus 36. Okay, the next step is to plot sigma y, comma, plus tau xy. So sigma y is equal to 60 megapascals. So we got 3, 4, 5, 6. There's 60 megapascals. And a positive tau xy is equal to minus 36. So 10, 20, 30, and 36 is right about there. So what I'll do now is I'll sketch a line between those 2 points, like such. So that was step 3, draw the line. And then step 4 is to draw a circle. Okay, so the center of the circle will be here, and we need a circle that fits between those 2 points. Easier said than done. Okay, let me try and sketch that circle in here. I'll have to freehand it the best I can. I can't use a compass, obviously, on my graphing tablet here, and I don't have a circle template that is big enough. So, and an artist I am not. So that is my circle, and I suppose I could cheat a little bit. Let's see, if I go up here to the top here, I could draw in a shape. Let's see. There we go. That circle doesn't look too terrible. All right. So then the next step would be to pick off the maximum shearing stress. So the maximum shearing stress always lies right above the center of the circle. So this is going to be that point there. That is tau max. And from my scale, that looks to be approximately 1, 2, 3, almost 4. I would say tau max is approximately equal to 38 megapascals. And then this is going to be either sigma max or sigma 1, depending on the notation. It is the principal stress, the maximum principal stress. And if this is, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So I'll call that to be equal to approximately 83 megapascals. And then the minimum stress is here. So that's either sigma min or sigma 2, depending on the notation. And that would be approximately equal to 7 megapascals using the scale. So those are the maximum and the minimums. And this line right here represents the original orientation of that state of stress. Now, if you wanted to know what the values of theta P and theta S are, they are like this. So we would have to rotate like that in order to get to the maximum shearing stresses. So this angle right here is 2 times theta S. And since we would rotate in a clockwise manner, with counterclockwise being positive, then that is actually minus. If we wanted the positive value, then what we would do is we would rotate like that, and that would be positive 2 times theta S. Okay, the subscript S stands for shearing stress. All right. if we wanted to know theta p, then we would go here. That would be 2 times theta p. Since we're rotating positive, that would be, or rotating counterclockwise, that would be positive. Okay. Okay, now let's suppose we wanted to look at the stresses that were on an orientation that was rotated by theta equals positive 40 degrees. So let's go down here and suppose that we wanted to look at some orientation where theta is equal to a positive 40 degrees. So this is the original orientation right here, this line. So what we would want to do in that case is we would want to measure and strike a line that creates an angle at 2 times 40 degrees from that. So I can use my protractor here, and let's see, 2 times 40 degrees is 80 degrees. So that means that I would want a line that is right about there. So if I sketch my line in like this, then that line is the rotated, and this angle, let me get rid of that balloon, this angle right here represents 2 times 40 degrees equals 80 degrees. So in that situation, then this value right here, then if this was, so this value up here was sigma x comma minus tau xy, then this value down here goes to sigma x prime comma minus tau xy prime. This value over here goes to sigma y prime comma plus tau xy prime. Okay, and we could pick those values out if we needed to, but we don't need to do that for this example. Okay, and finally, if we go ahead and look at the solution to this problem, then you can see this sketched a little bit more clearly. That is the Mohr circle that appears in the PDF version of this example problem. All right, great. Hope that helps.